All right, so when you are watching this, if you watch it on Wednesday, I will be interviewing Asian language professors as part of one of my university committee assignments. So I would rather be here in this classroom lecturing to you, but this is something I only have to do once a year, so it's only going to impact us on Wednesday. We'll be back to normal on Friday. A reminder that we are having a quiz on Friday, so make sure you take good notes in this lecture. We'll be talking about, so we introduced organometallics on Monday. Today we're going to be talking about their reactions with ketones and aldehydes. That's going to bring up a topic that we'll spend a little time on called protecting groups. That's how we can mask one functional group so that it doesn't interfere with a reaction that we want to do. And then we'll talk about organometallics reacting with carboxylic acid derivatives. So at the end of class on Monday, we taught you that our three organometallics, our organolithiums, our organomagnesium or Grignard reagents, and our organocuprates are all strong bases. So they will all deprotonate water to make hydroxide. It's a really expensive way of making hydroxide. So usually that's not the reaction that you want to perform. However, there's one example written here on the board where that's actually a useful process. So if you have an alkyl halide, and actually it can be alkyl aryl vinyl, if you have any kind of a halide, and you need to remove that halide, you need to reduce it and replace that halide with a hydrogen. The easiest way to replace that halide with a hydrogen is to make the organometallic. So you would be using either lithium or magnesium, doesn't matter which one. Magnesium's easier to work with, so most people would use magnesium. And then once you have your organometallic, you treat that with water. And now you have replaced your halogen with a hydrogen atom. So we don't often need to do this, but sometimes we do. Sometimes we have extra halogens in molecules we need to get rid of. And this is the easiest way to do that. You do form hydroxide in this case as a byproduct. That's not what you're looking for. It would be if you're looking for this product, which would either be an alkane, an alkene, or a benzene ring, where we've removed our halogen. So occasionally we use the basic properties of organometallics to good use, but most of the time we're using them as nucleophiles. This is where they're really valuable because they are nucleophilic on carbon, and so they allow us to form carbon-carbon bonds, which allows us to make longer chain molecules from smaller building blocks. Back in 351M, the one way we learned to do this was using acetylides. We would alkylate acetylides with primary alkyl halides or by ring opening of epoxides. Here, we're going to react our organometallics with a variety of species. So the first one I've drawn for you here on the board is the reaction with aldehydes or ketones. And this is going to be comparable to the reduction mechanism, but we're using a carbon-based group instead of a hydride, forming a carbon-carbon bond, generating alcohols, generating secondary alcohols, typically from aldehydes, and tertiary alcohols from ketones. With our simplest aldehyde, which is formaldehyde, our one carbon aldehyde, then we can make a primary alcohol. Right? So if you react this with a Grignard or an organolithium, you would generate a primary alcohol with one more carbon than that organometallic reagent. We can also react organometallics with our carboxylic acid derivatives. We cannot react them with carboxylic acids themselves because they'll just undergo acid-base chemistry. But with esters or acid chlorides, they will react. And just like we saw with the reductions, there are two possible products depending on which type of organometallic we use. If we use an organocuprate, you'll obtain a ketone, an unsymmetrical ketone with two alkyl groups. If we're using Grignard reagents or organolithiums, will generate a tertiary alcohol wherein two alkyl groups have added, two of the same alkyl groups have added. So this will differ depending on the organometallic that we use, and this only works for acid chlorides or ketones. It won't work for amides. It won't work for carboxylic acids because those will undergo just acid-base chemistry. We can also react our organolithiums and Grignards with carbon dioxide. This is typically done in the form of dry ice, just adding some chunks of dry ice to your organometallic species. Then we need to add aqueous acid, and when we do that, we end up with a carboxylic acid with one more carbon than the original organometallic species. And then our last reaction of organometallics, we'll probably get to this one on Friday. I should mention we're not totally finishing chapter 20 today. We'll finish it on Friday and then start 21. We can also open epoxides with organometallics. And this is not necessarily an epoxide with 4-methyl groups. These could be any combination of alkyl groups and hydrogens. And then we would add water, and we would end up opening that epoxide, generating an alcohol. And again, these groups, I'm not defining them. They're either some combination of alkyl groups and hydrogens. But we've now added 2 carbons from our epoxide and this alcohol to our organometallic species. So that's our overview of reactions of organometallics. Let's delve into more detail of the reaction of Grignards and organolithiums with ketones and aldehydes. So we have a mechanism here on the screen that we'll take a look at. This mechanism is the same as the mechanism of reduction of aldehydes and ketones. But instead of having a borohydride or an aluminum hydride, we have some sort of carbon-based group. Remember I said that can be alkyl, aryl, vinyl, alkynyl, any kind of carbon-based group. And then we have either a magnesium or a lithium. But this bond is polarized towards the carbon, so this acts like a carbanion. And we're using the electrons in that carbon-metal bond to attack the carbonyl, push the electrons up onto the oxygen, and then in step 2, we add water to protonate that. Right, this is going to make a salt with the cation here, but then we protonate it. The hydroxide byproduct makes a salt with the cation, and here's our alcohol. Okay. It's important to make sure, just like it was with lithium aluminum hydride, to do this sequentially, to add your water after the Grignard reagent is consumed, because if you add it together with the Grignard reagent, it'll just react in a very rapid acid-base reaction, destroying your Grignard reagent, providing an expensive way of making hydroxide and not touching your aldehyde or ketone starting material. Okay? So we have to keep water out of the reaction until this first step is complete. So let's talk about stereochemistry of this reaction. So, of course, if we're using formaldehyde, we're going to make a primary alcohol that's achiral. But let's say we're reacting with any other kind of aldehyde. And that's going to give us a secondary alcohol. So as long as the R group on our aldehyde and the R group on our reagent are different, then we're going to end up making a chiral secondary alcohol. Okay. Okay, we'll go ahead and draw stereochemistry. So this will be racemic. Anytime we form a chiral product from achiral starting materials, we get a racemic mixture. One of these products would be formed from our organolithium approaching from the top face of that aldehyde as I've drawn it. The other enantiomer would be formed by attack from the back face. There's no difference in those two faces. The rate of reaction is the same. And so we end up getting a one-to-one mixture of these enantiomers. If we're reacting ketones, then the outcome depends on if it's a symmetrical ketone or an unsymmetrical ketone. Okay? So let's take cyclohexanone. We're going to react that with an alkynyl lithium in this case, followed by addition of water. Because our ketone is symmetrical, our product is achiral. Right, we have a plane of symmetry in this alcohol, so I didn't draw wedges and dashes. So in this case, we get an achiral tertiary alcohol because we used a symmetrical ketone as our starting material. If we have an unsymmetrical ketone with two different R groups attached, here we've got a propyl group and an ethyl group. And in this case, let's react with Grignard reagents. We can just interchange Grignard reagents and organolithium reagents. As I mentioned on Monday, they react it's the same, very similarly. So we get a tertiary alcohol. Now it's chiral because we have four different groups attached. We had two different groups in the starting ketone. And so here, we end up with a racemic mixture of this alcohol because there's no difference in the rate of our Grignard reagent attacking from the top face of this ketone versus the bottom face. Okay. So what would we need in order to make a single enantiomer of one of these chiral alcohols? Well, we would need either a chiral catalyst or a chiral reagent. So remember, with our CBS reagent, we can obtain a single enantiomer of a secondary alcohol by reduction of a ketone. There are chiral versions of organometallics that can enable us to generate a single enantiomer of a chiral alcohol. This isn't in your textbook, but we'll just briefly take a look at this. This is a reaction we did in my lab. We published it now about 12 years ago, I guess that is. We didn't invent this reagent. This chiral organozinc reagent was developed by a Japanese chemist. Here's the part that makes it chiral. This reagent is comparable in reactivity to a Grignard reagent. So an organozinc reagent will react with ketones. We needed a single enantiomer of this alcohol in one of our multi-step syntheses we were doing. And we were very glad to find that this reagent developed in Japan gave us a good yield of that product and a very good EE, 95% EE. That's better than 95.5 in terms of the ratio of enantiomers. So there are chiral versions of Grignard reagents, chiral organometallics, that can give us single enantiomers of chiral alcohols, tertiary alcohols in this case. So some examples from the textbook. These reactions widely used in synthesis, some of the most widely used reactions because of the importance of carbon-carbon bond formation. If you remember back from 351M, and ethynyl estradiol was one of the first birth control pills. And so we can prepare that by Grignard addition to this, or organolithium addition to this ketone. Sadly, what they've left out in this case is the stereochemistry. This is a chiral molecule. They should have put in all the stereocenters. And so we would expect this reaction to be stereoselective because one face of this ketone is more hindered than the other. So in fact, this methyl group should have a solid wedge. It should be pointing up, shielding the top face of that ketone, directing that organometallic to the back face, the less hindered face. It would react faster. So you would have a major diastereomer. Sadly, they didn't draw that in. Here's another one where they left out the stereochemistry. And what we see here is something interesting. We have a ketone and we have an ester. And much like we learned on Monday that aldehydes react faster than esters in reduction reactions, ketones are going to react faster than esters. Ketones are more electrophilic than esters. So if you use one equivalent of your Grignard reagent, it's going to react with this ketone and not with the ester. Okay? And there's a stereocenter here. So again, you'll have a major isomer and a minor isomer. We won't predict which. That's a subject for a more advanced organic chemistry class, Chem 553, one of my favorite classes to teach, where we kind of pick up where 351 and 352 leave off. Usually it's first-year graduate students and seniors who are planning on studying organic chemistry for their PhD that take Chem 553. In that class, we would be able to predict the major diastereomer of this reaction based on stereochemistry at this site. But for now, we'll just recognize that there will be a major isomer and a minor isomer because this is chiral, and there's a stereocenter here that's going to shield one face of that ketone more than the other. But going forward, they then converted this into an epoxide. Once you have a vicinal halohydrin, you can treat with a base. Potassium carbonate is one of the weaker bases that can do this, but you could use potassium carbonate to deprotonate this alcohol and displace the chloride to make this epoxide. So a couple examples of how forming carbon-carbon bonds using Grignard reagents or organolithiums is important in multi-step synthesis. All right, so let's think about how we would use these organometallics in a retrosynthetic fashion. Let's take this secondary alcohol, and if we're going to make that from addition of a Grignard reagent to an organometallic, what we need to do is we need to go to the alpha carbon, the carbon that's bonded to the oxygen, and then we need to break one of the carbon-carbon bonds to that alpha carbon. I've drawn a symmetrical alcohol here, so it doesn't matter which one. So let's break this one here. And these three carbons are going to come from our aldehyde. And these two carbons are going to come from our organometallic. Okay? So this could be a Grignard reagent or an organolithium species. Okay? So this is a symmetrical, it wouldn't have mattered which of these bonds we would have broken. We would have ended up with these same two building blocks, 3 carbons and 2 carbons. If we have an unsymmetrical alcohol, then we end up with more than one possibility. So this is just a practice iClicker question since you're not here in the room, but you can go ahead and hit pause on the video and decide which of these 4 combinations of Grignard reagents could be used with an aldehyde to make the following alcohol. Okay? All right, hopefully you've come up with the answer now. If we need to break the carbon-carbon bonds between the alpha carbon and the beta carbons, so if we break this bond here, we would have benzene ring, 2 carbons, and then our organometallic, so that would be this species. So we can narrow it down to B or D. Then if we were going to make it the other way, we would break this bond, and we would have 4 carbons here and have our Grignard reagent. And so that would have to be this one, right? The one down here only has 3 carbons. And so it is B. B are the 2 different Grignard reagents that you could use to react with an aldehyde to make the following alcohol. We didn't ask you what the aldehydes would look like. If you use this Grignard reagent, you would use one aldehyde. If you use this Grignard reagent, you would use the other aldehyde. So you ought to be able to draw the aldehydes that you would use, that you would combine with either of these Grignard reagents to perform that reaction. Okay? So let's talk about a problem that we have sometimes when we are reacting organometallics with aldehydes or ketones. That problem is interfering acid-base chemistry. So let's say that we have a ketone, and that ketone has an alcohol attached to it. And what we want to do is we want to react the ketone with an organometallic. We'll just choose a Grignard reagent in this case and add water. So what we're trying to do is make a tertiary alcohol from our ketone. Okay. This is our desired product. We don't get this desired product. This reaction does not happen. No reaction. Well, I shouldn't say no reaction. I'll erase that. We do get a reaction, but we do not get the desired product. Okay? What's going to happen? I'm going to go ahead and draw this out. This OH is a weak acid, but it is acidic enough that it's going to react with our strongly basic Grignard reagent. Okay? So we're going to deprotonate. Acid-base reactions, we mentioned this in 351M, are the fastest intermolecular reactions we have because a proton is the smallest nucleus. There's no steric hindrance. So removing a proton is the fastest thing you can do from an organic molecule in an intermolecular process. Okay? So that's going to happen faster than the Grignard reagent attacking the ketone. And so you're going to end up with an alkoxide salt, and you've just made methane. Right? Methane's a greenhouse gas. Not only did you not get the reaction you wanted, you just contributed to global warming by making methane. So this is not the process that you want. Okay? So there's no way to add Grignard reagents to molecules that have OHs, that have carboxylic acids, SHs, NHs, because this acid-base chemistry will interfere. So how do we get around this? We use a protecting group. And this is the general concept of protecting groups. We'll talk about specific protecting groups in a moment. What you do is, in the first step, you're going to react your alcohol with a species that will remove the acidic hydrogen and attach some other group temporarily to that oxygen. So now there's no more acidic hydrogen. Now you can perform the Grignard addition. Add your reagent, add water, you get your tertiary alcohol. Step 3 is called deprotection, where we remove that temporary group on the oxygen, replace the hydrogen, and now we've made the product we were looking for. Okay? So what protecting group do we use? There's lots of protecting groups, actually. There's a huge book of protecting groups for various functional groups. You could spend an entire year learning protecting groups. But we're going to focus on just one common protecting group that's used for alcohols. Probably the most common protecting group. And that is a special type of ether. It's a silyl ether, where we have an oxygen-silicon bond instead of we have an oxygen-carbon bond over here, and an oxygen-silicon bond over here. There are actually lots of different silyl ethers that are used, but the most common one is the one we're teaching you now, and that is known as the tert-butyl dimethylsilyl ether, right? Tert-butyl dimethylsilyl. That is a mouthful, so we abbreviate it as TBDMS ether. That's how your book abbreviates it. We love abbreviations in organic chemistry, so we've actually abbreviated the abbreviation, and many people would just refer to it as a TBS ether. I'll try to write TBDMS to be consistent with the book, but if I slip up and write TBS, that's not the TV station. That means it is a tert-butyl dimethylsilyl ether. So how do we make this kind of an ether? Well, we learned in 351M to make ethers by Williamson ether reactions. Okay? So we're going to make a silyl ether by a modified Williamson ether reaction. We're going to take our alcohol. We're going to react our alcohol with a silyl chloride. Okay? All right, this is a good leaving group attached to our silicon. So we take TBDMS chloride. Right, we can call this TBDMS chloride. And we're just going to do an SN2 reaction here on the silicon, displacing our chloride. And this might look funny to you, because this is an awfully hindered silicon. We've got a tert-butyl group, we've got two methyl groups. This is like a tertiary alkyl halide. And we're doing this reaction with a weak nucleophile. We haven't even deprotonated our alcohol. So how can we get away with this? There's two reasons why this works. One is because silicon is a bigger atom than carbon. The bonds to silicon are longer. So these three alkyl groups are further away, much further away from that silicon than they would be from a carbon. Okay? So this tert-butyl group is not very close to the silicon. So this silicon is not as hindered as it looks because of those longer bonds. Okay? Our second feature is that silicon is less electronegative than carbon. So this silicon-chlorine bond is more polarized. Even these carbon-silicon bonds could be weakly polarized. So we've got a significant partial positive charge on that silicon. So for both electronic and steric reasons, this reaction works with a weak nucleophile, and that gives us the conjugate acid of our TBDMS ether. Okay? And then we use a weak base. We use imidazole as a base in this reaction. We learned about imidazole. And let's see, we want to use this nitrogen. Remember, imidazole is a five-membered aromatic heterocycle. We'll draw both those lone pairs in. This lone pair is part of the pi system. It's less basic. This lone pair here is the one that is actually a decent base. So that deprotonates this product, gives us our silyl ether, and generates an imidazolium cation. And that imidazolium cation is just going to make a salt with our chloride. Okay? So this is how we make silyl ethers. Okay? TBDMS chloride and imidazole. Okay? So that's going to go in step one, those two reagents. How do we take off the silyl ether? At step three, we've got to remove that silyl ether. How do we do that? We use a reagent called tetrabutyl ammonium fluoride. Okay, tetrabutyl ammonium, I'm going to draw for you here. This is the tetrabutyl ammonium cation. Here's the fluoride ion. Tetrabutyl ammonium is an organic soluble cation. That's the reason for these four butyl groups, to make this cation dissolve in organic solvents. With our love of abbreviations, we refer to tetrabutyl ammonium fluoride as TBAF. All right, so you see TBAF, and that's this species. It's an organic soluble source of fluoride ion. Okay, why do we want fluoride ion? Well, if we have a silyl ether, such as a TBDMS ether, and we react that with fluoride ion, that fluoride ion is like a heat-seeking missile for silicon. It's going to seek out a silicon atom and attack that silicon atom and displace our alkoxide. Okay, so we're going to get an alkoxide. Okay, we've also produced, I'm just going to abbreviate those alkyl groups, a silyl fluoride. And then to get the final product, we need water. And there's always water. Whenever you have TBAF, even if it's dissolved in organic solvent, it's always going to have water. You're going to have ion dipole interactions. There's always going to be water present. And so the water that comes along with the TBAF can protonate your alkoxide and give you your alcohol back. Okay? So why does this fluoride attack the silicon? The silicon-fluorine bond is incredibly strong. Okay? The bond dissociation energy is 158 kilocalories per mole. Most sigma bonds, carbon-carbon, carbon-hydrogen sigma bonds, are in the 90 to 100 range. Okay? So this is significantly stronger than the sigma bonds we're used to dealing with in class. So because the silicon-fluorine bond is so strong, fluoride acts like a silicon-seeking missile, selectively reacts with fluoride, or with silicon, to generate this very strong bond, displacing this group and restoring our alcohol. Okay? So, and the nice thing is, tetrabutylammonium fluoride hardly reacts with anything else except silyl ethers. So it's a very specific reagent, very useful. So we see here how we can specifically use protecting groups in this sequence that we showed you generically previously. Step 1, TBDMS chloride and imidazole. That puts our protecting group on. Step 2, we add our Grignard reagent to the ketone, followed by water. Step 3, tetrabutylammonium fluoride cleaves off our silyl ether, revealing the desired diol product. Okay? Protecting groups are useful, but they're also a necessary evil, because every time you use a protecting group, you add 2 steps to the length of your synthesis. You add a protection step and a deprotection step. So we usually try to make our syntheses as short as possible. So we try to avoid using protecting groups when we can, but when we can't, they're useful. They enable us to do reactions we could not perform without them. All right, let's talk now about carboxylic acid derivatives, our acid chlorides and our esters, reacting with Grignard reagents and organolithiums. So these reactions, first of all, are going to require 2 equivalents of our organometallic. So here I've drawn it with a Grignard reagent, 2 equivalents. Then we add our water. And what we're going to get from this reaction is a tertiary alcohol with 2 of the same R groups. Okay? So both equivalents of our Grignard reagent are going to add to our acid chloride or ester, and they're going to give us a tertiary alcohol in this case. So let's look at the mechanism. And it's a familiar mechanism. Shouldn't be any surprises here. So step 1, just like we saw with aldehydes or ketones, The Grignard reagent is going to react, adding to the carbonyl, giving us our alkoxide. So this is our tetrahedral intermediate. We've seen tetrahedral intermediates in the reductions of carboxylic acid derivatives. Okay. And we know that this Z group is a good leaving group, especially when it's less basic. Whether it's a chloride or whether it's an alkoxide, it's going to be less basic than our Grignard reagent. So we're going to be able to eliminate Z. Okay, eliminate the anion of Z, either chloride or alkoxide. And that's going to give us a ketone. Okay. Now, the ketone is going to be more reactive than our ester, certainly, and of comparable but slightly higher reactivity than our acid chloride. So once we generate our ketone, that's going to react with a second equivalent of our Grignard reagent. Okay. Now we no longer have a leaving group on this species, so now we add our water to protonate the oxygen, and we end up with our tertiary alcohol. Okay. And we formed hydroxide in the process, and that hydroxide is simply going to make a salt with the magnesium from our Grignard reagent. Okay. So if this is an ester, the ketone intermediate is more reactive than the ester that we start with. So as soon as we form this, it's going to react fast. It's going to react faster with our Grignard than the ester would. So if we had one equivalent of our Grignard reagent, we would end up with a 1-to-1 mixture of unreacted ester and tertiary alcohol, because as soon as this ketone is formed, it's going to get consumed. And then once we run out of Grignard reagent, we're going to have a 1-to-1 mixture of these two species. Okay. Now, acid chlorides are close in reactivity to ketones because they're the most reactive of our carboxylic acid derivatives. So there, you'd probably have a messier situation where you'd have comparable rates of consumption of the ketone and the acid chloride. So you'd probably end up with a mixture of all three of these. The take-home message is the reaction of one equivalent of a Grignard reagent or organolithium with an acid chloride or an ester is not going to be useful. You have to use two equivalents to make sure that you drive all of the material to that final tertiary alcohol. So it's only useful when you need a tertiary alcohol with two of the same R group. So if you're ever asked at any point, either in real life or on an exam, to make a tertiary alcohol with two of the same group, then a light bulb should go off into your head and say, I can put those two propyl groups in this case on via a Grignard reagent, and then I can get the remaining part of the molecule from an ester or an acid chloride. And then here's how you would do that synthesis. In the synthetic direction, you would not have to add these separately. You would add both equivalents of the Grignard reagent at the same time, followed by adding water in a second step. So we can make ketones, however, from acid chlorides, and we do that using our organocuprates. Okay. So we can react acid chlorides with organocuprates. I told you that organocuprates have different reactivity from our other organometallics. And here's where they will react. They will react with acid chlorides, followed by the addition of water. And that generates our ketone. Okay. So these are less reactive, and they're actually a different kind of reactivity. The mechanism of these organocuprates reacting with the acid chloride is different from the mechanisms of our organolithiums and our Grignard reagents. So our organocuprates actually don't react with ketones or aldehydes. So that seems unusual. No reaction with ketones or aldehydes, only reactions with acid chlorides. That's because they require this carbon-chlorine bond. The special mechanism that they react by depends on the presence of a carbon-chlorine bond. Okay, so we're not going to learn that mechanism in this case. We'll learn other mechanisms of organocuprates, but not this particular reaction. You might wonder, what's the water doing? Right? There's nothing to protonate. The water is just quenching byproducts that you get from this reaction. Okay, so you don't need the water to put a proton in the product, but you do need it to quench those byproducts to be able to separate them from the desired ketone. Okay, so we can look at a sample problem, and that sample problem is going to show us how we could use two different combinations of acid chlorides and organocuprates to generate an unsymmetrical ketone, 2-pentanone in this case. So in the retrosynthetic direction, you would cleave either of these carbon-carbon bonds to the carbonyl carbon, and that would give you two pairs of reagents, either of which would be viable, either of which would be useful to make the ketone. Okay, so that's our first reaction of organocuprates that we're learning. We'll learn another one at the end of class or at the beginning of class, sorry, on Friday. So one more reaction we're going to learn of organometallics, not involving carboxylic acids and their derivatives, but involving a related compound, the only carbon compound at a higher oxidation state than our carboxylic acid derivatives, is carbon dioxide. And carbon dioxide can react in similar fashion to carboxylic acid derivatives. It has two carbonyls jammed together. And so carboxylic acid, carbon dioxide can react with organolithiums or Grignard reagents to generate carboxylic acids. And we'll start with the halide, just to show you how this process goes. Bromine, chlorine, iodine, it doesn't matter. So you would react that halide with either magnesium or lithium. I mentioned that magnesium is more convenient to work with. So if given a choice, I would choose magnesium. Now we have our Grignard reagent in this case. We're going to react that Grignard reagent with CO2, followed by the addition of aqueous acid. And that's going to give us a carboxylic acid, benzoic acid in this particular case. So now we have two different ways of making benzoic acids. We can either use KMnO4 to oxidize an alkyl group, or we can make this Grignard reagent and react it with CO2. Okay, this is adding a carbon. And it doesn't have to be a benzene ring. You can do this with alkyl groups, vinyl groups, any of those types of groups, and add a carbon and have it be a carboxylic acid. So let's just look at the mechanism of this process. So here's our Grignard reagent. Here's our CO2. We have two carbonyl groups pulling electrons, two oxygens pulling electrons away from the carbon of CO2. Right, so this has a fairly substantial partial positive charge on the carbon. So it shouldn't be too surprising that our Grignard reagent can attack the carbon of CO2 in the same way that it would attack the carbon of a carbonyl compound, an aldehyde, ketone, or carboxylic acid derivative. And then that's going to give us a carboxylate. This is our conjugate base of a carboxylic acid. And we have a salt. I'll go ahead and write, there's our cation that's going to form a salt with that species. But then we're going to add our aqueous acid, our H3O plus, to protonate this. Giving us our final carboxylic acid, and of course water is a byproduct. Okay. So when we protonated alkoxides, we used water. Why do we have to use aqueous acid in this case? This carboxylate is a much weaker base than an alkoxide. So if you were to add water to this, it's not going to protonate. Right? You're not going to protonate a carboxylate with water because then you'd be forming hydroxide, which is a stronger base than this. Okay? So we can't just add water to our carboxylate because we wouldn't be able to protonate it. So because it's more weakly basic than an alkoxide, we have to add H3O plus to protonate it to make the carboxylic acid, and then we generate water as a byproduct. Okay, so we'll stop there for today. Remember, we have the quiz on Friday, covering largely what we talked about in this lecture as well as Monday's lecture, maybe a little bit from the part we did on Friday. And then on Friday, we will finish this chapter. We've got a couple more reactions to talk about in chapter 20, and then we'll move on to chapter 21.